Okay, so we are going to move on to our first panel speaker of the afternoon, and this is Timi Ojo. Timi Ojo is the current agricultural systems modeler with the Department of Agriculture and Resource Development of the province of Manitoba. Prior to his current position, he was the provincial agro-meteorologist between 2015 and 2019, where he led the expansion of the Manitoba Agriculture Weather Programme from a network of 46 to 108 weather stations. Timi obtained his PhD from the Department of Soil Science at the University of Manitoba, where he conducted research on how weather impacts agriculture. He specifically focused on in situ, proximal, and remote sensing soil moisture determination, soil moisture sensor calibration, measurement, and modeling.
I'm so glad to be here today. This presentation will provide recent weather trend in the context of historical prairie climate, and also discuss the wildcard effects, which are often hard to predict. So starting from a global context, NOAA's global land and ocean temperature anomalies shows the annual global trend deviation, the temperature deviation, compared to the 20th century average. It's important to note the most recent trend, starting from the late 70s, and in fact, the top 7 warmest years have all occurred in the last 7 years, and last year was the second warmest. Bringing it closer to home, this chart for the land temperature deviation in North America compared to the average of last century, and since 1997, we have not had annual land temperature below the 1910 to 2000 average, and last year claimed the 10th spot. Let's look at the trends on the Canadian prairies, again bringing it further closer to home, using data from 3 prairie cities. The annual mean temperature trend at this regional scale on the prairies is actually very similar to what we have observed on both the global and the continental scales. Eastern Prairie is warming up slightly faster than the other parts of the prairies, and generally, we are warming at slightly more than 1/4 of a degree every 10 years. All 3 cities shows a warming trend. For agricultural purposes, especially for crop production, we know that the growing season months, usually between May till October, are very critical. One of the master students at the University of Manitoba, Cody Olsen, analyzed the trend of corn eat units at 12 prairie locations, 4 locations in Alberta, 5 in Saskatchewan, and 3 in Manitoba, all locations that have long-term historical record. And used the World Meteorological Organization climate normal delineation, that's a 30-year climate normal, to divide the data set into 3 periods. And the goal was to check if there were significant differences in the corn eat units. Although there were some spatial variabilities across the location, its results showed a cooling trend in the useful heat accumulation in the first period between 1930 and 1959. There was a slight warming trend in the second period, and in the most recent period from 1990 to 2019 actually showed a much bigger warming trend. Statistically, both the second and the third periods were significantly different from the first period. The monthly breakdown of the most recent period, again between 1990 and 2019, actually showed that the warming trend during the growing season was only significant in late spring and early summer. So in June and July, those 2 months, as indicated by this red line, were the 2 months that actually showed a significant warming trend. Now, we know that temperature isn't the only factor. Water availability plays a major role in terms of crop production on the prairies. Now, over the last 60 years, we have seen a slight increasing trend in precipitation, which is not significant at most of the locations across the prairies that we analyzed. Now, these 3 locations, Calgary, Regina, and Winnipeg, showed an increase of about 1/10 of an inch every 10 years. So just about 3 millimeters increase every 10 years. However, using this generic end of season total precipitation often mask the intra-seasonal moisture stresses that crops and livestock may experience. Now take a look at this chart from one of the Manitoba agriculture weather stations at Centerdorf, Manitoba. Centerdorf is about 15 kilometers south of Winnipeg. The climate normal precipitation between May and September, which is often the growing season in this area, is 355 millimeters. That's the 30-year average. Now, the total growing season precipitation in both 2016 and 2019 was about 400 millimeters, just under 16 inches. Now, looking at this data set, it may be easy to conclude that both years being well above normal precipitation, that there must have been at least adequate, if not excess moisture for crop growth. However, looking at the cumulative precipitation pathway tells a completely different story in terms of precipitation profile each year. Now, this is the cumulative precipitation at that location in 2016, and it was generally a good year with good moisture available for crops. Precipitation pattern actually followed the climate normal precipitation pattern, although during the harvest period, we received way more precipitation than many producers would have preferred. In contrast, 2019 was generally regarded as a dry year, despite the fact that the year ended at above historical average. Actually, my last pre-COVID extension event, the in-person event, I asked about 70 farmers last year and asked if they thought 2019 was a wet or a dry year. And almost unanimously, the response was that, Timi, it depends on when during the season. And that's because precipitation was limiting, especially during the critical stages where crops really needed. Actually, at this point in early July, we had about 100 millimeter deficit deviation from the historical average. And this is at this point where crops are actively at the vegetative stage and almost approaching the reproductive stages. The location had 3 storms, which accounted for over 60% of the total precipitation received that year. So sometimes, or most times, just using the total end of year precipitation cumulation often mask the intra-seasonal effect that we see. So the current trend and into the near future actually shows that there would be a decrease in crop heat limitation due to increasing temperature. We may be able to push agricultural region northward, although I would say for those that love chocolate, there's no cocoa tree yet, but we've seen increase in soybean and corn acreage driven mostly by improvement in genetics as well as the warming climate. However, this may also bring with it increasing water limitation as the warming trend tends to drive greater evapotranspiration. We know that precipitation trend is quite uncertain at this point. We may or may not see any significant shift in terms of total precipitation. However, we are seeing increasing variability in weather extremes. We've seen more hail, drought, flooding happening at higher frequency than we've seen in historical records. Actually, last year, the top 3 insured damage due to severe weather events occurred in Alberta here on the prairies. And we cannot discuss these changes without mentioning the catalyst driving the change. When you take a look at this chart, the storm of June 13, the Calgary hailstorm did cost about $1.3 billion. So we know that there are some catalysts that are driving this change. So these changes we are seeing correlate with increasing greenhouse gas emission, and data reconstructed from ice cores actually showed that the highest CO2 levels we had pre-1950 was 300 parts per million. We know here on the prairies, again, with the conversion of the prairie landscape to annual agricultural landscape in the early part of last century, at 1950, we were at 300 parts per million. Currently, we are at 415 parts per million. Now, we know that CO2 isn't the only greenhouse gas of concern. The other two main greenhouse gas to consider in agriculture, nitrous oxide from fertilizers and manure, as well as methane from livestock. So mitigation effects on the prairies have taken different forms, from improved livestock nutrition by the livestock industry, and then 4R nutrient management, looking at the right rate, the right form, the right placement, and the right time to help mitigate nitrous oxide losses. I'll briefly discuss some wildcard effects which are not specific to the prairies or even to agriculture, but cut across all sectors. And the first and foremost, technology. I think technology is going to play a major role in assisting us with mitigation and adaptation to climate change. However, it is difficult to quantitatively predict the impact that technology is going to have. An example is MethaneSat, which is a satellite to track global methane emission. I'm actually quite excited about this project because the data will be publicly available. At least that's what has been promised. The satellite will be launched next year, late next year, and knowing the amount, the timing, and nature of emission on a spatial scale can assist with proffering best practices to limit greenhouse gas emission in addition to mitigation strategies that are already being implemented. When you take a look at this image at the canyon in California, there's a natural gas facility situated right in the canyon. You can't see anything visibly from this facility. However, when you use an infrared thermometer, you would actually see the methane being emitted. And oftentimes, as humans, the rate and urgency of our action to mitigate an effect increases when we're able to visualize it. Another important wildcard is politics. Governments do change, and with a change in government usually comes about with a different agenda. And we've seen this firsthand across the border recently, where a single tweet can dictate the direction of the market. And this has huge influence on global trade and economics worldwide. And there are so many other wide factors that I currently categorize as others because they are unknown factors. One of such examples is COVID. And this chart from a paper published in Nature last spring during the early months of the pandemic showed a drastic reduction in global daily fossil CO2 emissions. And we were actually back to the 2006 levels. Now, I don't think anyone would have predicted this 15, 18 months ago. And despite this wild card, it's uncertain and the uncertainty surrounding their effects, we need to look at how can prairie agriculture adapt to these changes. Here are some adaptation tools Dr. Karen Wittenberg and Dr. Brian Amiro from the University of Manitoba suggest. And first and foremost, education is very important for producers and for many of us engaged in the agriculture industry. We need to develop a panoramic view, a broad systems approach. And because oftentimes when when professors and when we write proposals for research, we often write proposals to address one or two variables, but not looking at the system as a whole. And models such as OLOS can actually help to understand the impact of changing one variable on the whole system. And apart from gaining this knowledge, we should be willing to share the knowledge and information with the public, not just within the scientific community or the agriculture community. Another important tool is also policies. Policies need to be scientific based and can be implemented through legislation and regulation. I know across the prairies in many jurisdictions, many provinces, we have overwinter nutrient application ban, such that producers are not allowed to apply nutrients on frozen soils. So policies and legislation such as this can actually help as a very successfully adapting to climate change. And the final point I would discuss on this is innovations. Innovations should be science-based and technology-enabled. An example of that in managing intra-seasonal variability, is a picture of this farm that captures the runoff in the spring. It stores it and uses it for irrigation. And this is done on a farm level where it traps the nutrients that would have gone into the surface water bodies. This retention pond has been successful in removing excess soil moisture via trial drainage before seeding, and it allows for early access to seeding operation in the spring. It has also been successful and it's been used as an in-season water supply back to flood tiles drain. Now, the value of such a drain storage irrigation system continues to be studied. However, if this system is replicated on several farms, we need to understand what are the implications to stream flow and to habitat along the riparian areas. We also need to look at what's the optimum number of surface water reservoir, such as this retention pond, that a specific watershed can support. Now, these are some questions that our adaptation strategies need to innovatively answer as we sustainably ensure that food production continues on the prairies. With that, I'll be looking forward to an enriching conversation during the panel discussion. Thank you very much.